The last topic that I intend to talk about this semester with you, if only for the bonus homework, which is all that it's going to be on, is the topic of diffraction of light through a slit or a double slit or many slits. What do I mean by slits? I mean this. If you have a piece of film here, you can see, depending on where this piece of film is, right there I have two slits that the light can shine through. Above it I have one. Over here I have two slits, but they're spaced closer together, and above it I have one also. So I can show you if I actually shine a single ray of light, like a laser beam, such that it hits those slits, what is the pattern that's going to be created on a wall behind it, or a screen? I'll do the same thing for these things here. These are called diffraction gratings. They represent a lot of tiny slits, so many that you can't even tell. It looks like you can just see right through it. But you probably notice some sort of a rainbow feature. I'm going to shine some light on it. Probably notice kind of like, almost looks like diffraction like through a prism. But it's actually due to interference because the different wavelengths of light bend slightly differently as a result of interference, which is something that the multi-slit diffraction deals with. It's a way to separate light. And it's pretty amazing what you're going to see when you shine a single beam of light, like through a laser beam, through these different gratings. And I also have another grating here. When I say a grating, I mean it's like a grate, but really small. This one here has 100 lines per millimeter, 100 individual slits per millimeter. So imagine how small the separation is. This one is 300, this one has 600, and this one has 1,000. So there's 1,000 little slits in there over 1 millimeter. So there's more than 1,000 because that's a couple centimeters wide. So we're talking 20,000 slits or something like that are in that. And you can see the little rainbowish sort of pattern that happens there. So those diffraction gratings are really useful for breaking up light. And we can determine if we can see what kind of light things are glowing with. You can tell what materials are in them. They're useful in astronomy. They're useful even on the Earth where we're having really hot things glow. We can look at them through a diffraction grating and we can determine what elements are in whatever's glowing. So it's a very useful technology, and the physics behind it is fascinating, and it's what allowed us to determine that light has wave qualities to it. Light can be confusing. It can look like a particle. It can look like a wave. Diffraction gratings light was first shined through it, actually a double slit, by a physician named Thomas Young back in the 1700s, I believe. And from that, we later determined that light has wave-like qualities to it. So I'll be doing some demonstrations and showing you some slides on that. That'll help you on the bonus homework. It'll also help you think about a really important and useful aspect of physics. I'm shining a laser through a single slit on a piece of film here. And the distance between the slit and the screen, which is a door, is about 1 meter. And on the door, you can see the pattern that's coming out. It looks like that. That's the pattern from a single slit. You might ask, why isn't it just an image of the slit itself? It's because of the process called diffraction, which even light coming out of a single slit will spread out in this interesting way, which you can learn more about in a different class. I'm going to be looking more at a double slit. So I'm going to shine this green light through a double slit of a narrow spacing, of two different spacings, and you'll see what happens. Okay, this is a case of the green light now being shown through, or shined through, a double slit, which is at the bottom of this piece of film. There's a double slit. And this may look similar to you than the other one, but if you look very closely, you'll see little, small, tiny little fringes that are existing within there. Not the big ones. These are the big fringes here. Those are big fringes, but you'll see tiny little fringes in there. That's the result of the double slit. From a single slit, you didn't get those. Okay, now the green laser is being shined through slits that are actually spaced further apart from each other, and now you can barely see the little fringes in here, but they're there. But they're just much closer together, so they're so close they're hard to actually see the fringes that are. Now I'm repeating the same experiment, starting with a narrowly spaced two slits with red laser light. And here's the pattern. And here you can see much more clearly the fringes that each of the lobes has, which is a result of having two slits rather than one. And these two slits are very closely spaced. Now I'm going to make the slits wider apart, and let's see what happens to the fringes. Okay, here's the image of the two slits spaced more widely apart, and you can barely see the fringes. I can't really even see them now with this red light, this red laser light. All right, if I back up the film a little bit, I'll get a greater distance. I get greater resolution, and I'll be able to see the tiny little fringes in there. But what's interesting is as the spacing gets further apart between the two slits, the fringes get closer and closer together. It's kind of like the opposite thing happens on the pattern as what happens on the spacing of the two slits on the slide itself. Now I'm going to show you what the pattern looks like when I have the laser light shining through diffraction grating. So I have both red and green light shining through this diffraction grating. They're a little bit offset. They're not exactly at the same point because my two lasers are aligned like that. But on the wall, you can see the red are spaced, the red dots. There's a bunch of red dots. We're actually seeing a much more expanded view now of the bright spots that we saw when we had two slits that were much, much further apart than these gratings are. So now the bright spots are very well defined. But we can see that the green ones are closer than the red ones are to each other. I actually see 5 green spots now. I only see 3 red ones in this case because of the limit of how much the light can go away from the angle of the film here. But we see that the green are more closely spaced than the red ones. The reason for that is the wavelength of the green light is shorter than that of the red light, which is very interesting. This is a way that we can also separate light into its different color components, kind of like the prism, but using a completely different method. Okay, now I went from 600 lines per millimeter to 300 lines per millimeter. Look what we see now. We see quite a few more of the dots because the spacing is much more spread apart here. So the dots are going to be closer together than they were in the last case. So I see right now, gosh, I'm trying to count the green ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 green dots is what I'm seeing. If you look all the way over to the left side and all the way over to the right side. Maybe even 11, actually. There's one appearing on that can right there. And on the red, as far as the red dots, I'm seeing 1, 2, 3, 4, 5, 6, 7 of them. They don't extend again as far as the green ones do. Because the red ones are going to be more spaced out than the green ones, so I don't get as many in there. Again, the red light has a longer wavelength than the green light, so that's why we're seeing that effect. So now I'm at 100 slits per millimeter, and we see quite a few more of the green and red dots than we saw previously. Again, the red ones are spaced further apart than the green ones, so I see more green ones because more of them are going to fit in the aperture space that's available from the slit that's diffracting the light out and using the physics that we're going to talk about in a couple of minutes. Very pretty, of course, but it's interesting to see the distinction when we have two different colored lasers shining through the same diffraction grating at the same time. So if this were class, I'd ask you, it's shining through a diffraction grating again. Does this diffraction grating have more or less than the ones we saw in the previous slide? And the answer is this one has way more. This is 1,000 lines per millimeter. They're so close together that the dots are spaced further apart. Again, the red ones are spaced further apart than the green ones. And if you could actually measure and predict where those bright spots are going to be based upon the dimensions of the setup. How far away is this piece of film from the wall, and how many lines per millimeter are on the film, and what is the wavelength of the different laser lights. That would allow us to predict exactly where each spot's going to appear.